Okay, so we're going to write down the problem. This is just problem number 1 as an example. So in your notebook, you write down number 1, y is equal to negative 3x to the 4th plus 4 all raised to the 3rd power. Write that down. Make sure you write the y equals. I've already found some people not writing equations. You have to write equations because everything we do is based on equality. If you don't know what something is equal to, you really don't know how to proceed. Okay, so we've got an equation. We introduced a new operator today. We've used this operator before, but we've never used it to the depth we're going to use it. It's called the derivative operator. It's d over dx. So you write on your paper, we're going to simply differentiate both sides of this equation. Or you can say we're going to take the derivative of both sides of the equation. But it's just like algebra you've done before. You're performing an operation to the left side, so you must perform that same operation to the right side. The new operator looks like this, d over dx. Write that down, d over dx. And it operates on something. It's like the sine function. Like I'll write this over here. You've used this before. You have the sine of, say, x squared. This doesn't mean the sine multiplied by x squared. It's the sine operating on x squared. No multiplication here. This is also not multiplication. It's the derivative of, and we're taking the derivative of the left side, so it's the derivative of y. So just like this, just like the sine function. Again, this is not multiplication at all. No multiplication. It's the derivative of. Since we took the derivative of the left side of the equation, we must take the derivative of the right. So we just do the same thing. d over dx. Bigger parenthesis of, let's see, negative 3x to the 4th plus 4 all cubed. So that's step 1. We've taken the derivative of both sides. Talk, please, what you mean by both sides. Oh, if you have an equation, there's a left side of the equation, there's a right side of the equation. We are using the operator, and we're operating on the left side. Now we're using the same operator and operating on the right side. So both sides. Please.
And then the d over dx is the same as like whatever you're saying.
Thank you. It's close. 2 for Todd and 2 for Sarah and 2 for everyone else who makes a comment. F prime is going to show up in a second, but you're really close. This symbol here is often written in a more compact way like this. They mean the same thing. So this symbol means the same as this symbol. Questions? Okay, again, please emphasize 1 second. There is no multiplication. This is not d times y. This is not d times x. If it were, you could say the d's divide, but it's not multiplication. The symbol dy is like one symbol. You don't separate it. It's not 2 symbols, it's 1 symbol. Questions? Jeff, please.
Okay, so you're saying that dy over dx is the same sign as d over dx?
Of y, yes.
Okay.
Yeah. This symbol, you'll see it both ways, so I make sure I show you both ways so you can get used to it. So this symbol has exactly the same meaning as this one. Okay. Here's what Sarah noticed. I told you already that the symbol dy dx has another symbol that means the same thing. That's f prime. So you can write dy dx as dy dx, or you can write dy dx as f prime. They basically have the same meaning.
Would it be f prime of x, or do you mean f prime of y?
It's f prime of x, because this is a function in terms of x. So this is the derivative of that same function in terms of x.
Okay.
So f prime of x, that's y.
Say it again.
F prime of x is y. That's the same thing as the very first.
No. At the very beginning, we'd have to say this, Sarah, that this function could also be known as f of x. So this symbol is representing the y coordinate of this function. This is a different symbol, f prime of x. Somebody knows the answer. So what does the symbol f prime of x represent in terms of this function? You know this already. You just got to remember it, Sarah.
The slope of that at every single.
Perfect. So this symbol represents the slope of the function f at every point. Okay, perfect. Chuck?
Wait, so you said like the f prime of x represents slope, so does dy over dx also represent the
Yes,
slope?
they have exactly the same meaning. Exactly the same meaning. In fact, this symbol is easier to identify why this symbol means slope, because there's no multiplication occurring in this symbol, but there is division. It's the change in y, the infinitesimal change in y, that's what the dy means, divided by the infinitesimal change in x. Please.
So it's, just to get this straight, so f prime is the slope of f, whatever. Okay, cool.
Perfect.
Will we ever see it as delta y or delta x?
Oh, great question. The symbol delta x over delta y is a symbol for the secant slope. So the secant slope is always change in y divided by change in x. The tangent slope is really the same formula, except that it's done with points that are infinitesimally close to each other. That's what the dy means. So the symbols are extremely related. There you go. Awesome. Okay. Okay, so we figured out kind of this side. Oh, one other thing I need to point out. The dx on the bottom is crucial. For our class, we always find derivatives in terms of the input variable of the function we're dealing with. So in this case, we are dealing with a function whose input variable is x. Therefore, this becomes dx. This becomes dx. Please.
So instead of like x and y, it was like g and h, where h is in the y spot, it would be like d over dg times h.
You got the right idea. I'll take an example that's a little more common, but you got the right idea. Perfect. So Landon. A common example would be if I have a formula for velocity, and the velocity is something like, I'm just making this up, 25t cubed. If we take the derivative of both sides of this equation, Landon, what is the input variable in this case?
V and t.
The input variable
It
is
would be
just t.
yeah.
So you'd write the derivative of, so you'd say d over dt of v of t. Come on, guys. Like that. D over dt of this thing. Like that. So you're taking the derivative in terms of t. Other question. Okay, another thing. The d does not mean derivative. The d actually means infinitesimal difference. Difference means you subtract two things. Derivative is the whole thing. What I'm circling right now, that means derivative. So the way I read this is the derivative of v of t.
Is f prime of x the derivative?
Yes.
So why are they different than like, if f prime of x, why is it different than d over dx of y?
It's historical, Sarah. Different mathematicians came up with different symbols, and they were never able to simply settle on one symbol. So now you have to learn two. So we'll just
But
lay
they
it
mean
down.
the same thing.
They mean the same thing. So this means the derivative of the function y in terms of x.
Okay, I mean like the one
Oh, sorry.
above that though, like the function.
Up here?
Yeah, that one.
Oh, same thing again.
Okay.
Yeah, so this symbol means the same as this symbol, means the same as this symbol.
So like on the other side of the equal sign, would it just be equals, like could you do dy over dx equals d over dx and then like.
We could do this, maybe, I'm not sure what you're thinking, but, so are you okay that when we have this function, they said we want to apply the derivative operator to both sides. So do you feel comfortable getting from here to here?
Yeah.
Good. And then I said, it's just a little easier to write this like this. We can do something similar here. I've seen this written before. Just d negative 3x to the fourth plus 4 all cubed all over dx. That means the same thing. Is that what you meant?
Yeah.
I do?
Yeah.
Okay. Anybody else? Questions? Okay, next step. We've got to figure out how to use this operator. So this is where you get out that blue sheet I gave you in the sheet protector. I need to pull up a file on my computer, 1 second.
Wait, was it
'That was his only
She just gets all of it.
She was so sad.
How much you bought?
Oh, Misha.
I was got seconds.
Okay, look up now. Okay, okay, come back. Okay, we've got to figure out how to apply this operator to this situation. That's what the blue sheet is for. So if you look at the blue sheet, make sure your phone is put away from you. If you look at the blue sheet, you're simply looking at the left side of each rule. And you're trying to find something that matches with the situation that you're dealing with currently. So for example, we're trying to find the derivative of this thing here. So I'll point out some that are usually easiest to see to start with. We're not finding the derivative of the tangent of something. Agreed?
Yeah.
We're not finding the derivative of the inverse cosine of something. We're not finding the derivative of the natural log of something. We're not finding the derivative of e to some power. Somebody can probably see it by now. What do we find the derivative of? Like it fits one of these patterns. And you're only looking at the left. Don't look at the right, just the left-hand side is where you look. Somebody can see it. Glenn,
Is it either the power or the chain rule?
the chain rule? This one looks kind of like it could be what we have. We just have something just a little bit simpler. Just a little bit simpler, 2 tickets, top. It's not the e rule because we don't have e to this something. Like if we look back here, derivative of, there's no e anywhere here, so we know it's not that one. These are all worth 2 points. Let's go, Sarah. The power rule is the one we need to use. So I'm going to write that down here so we don't have to keep writing it on both sides. The power rule says, let's write this one here, black word. So the power rule says the derivative of, ddx means derivative, something to a power can be written as number times the something n minus 1 multiplied by derivative of that same something. This is the power rule. You all have it on the blue sheet. If we're going to use the power rule, we have to identify what the exponent is and what is being raised to the exponent. So someone help. What's the exponent in our situation? What's the n? And what is it that's being raised to that exponent? Looking for a hand. So if I,
Is it 4 and then 3?
so what's the n you said?
3.
N is 3, perfect. That's this one here. And then Heidi. What exactly is being raised to the third power?
Negative 3x to the 4th plus 4.
Perfect. That's this thing.
Okay.
That's this, I will refer to it as the something. That's what my college teacher called it, the something. So we've got something to a power. Please remember, I taught a lot of you this recently in days working on test corrections. Equal doesn't mean here comes the answer. Equal means same as. So we can take whatever's written like this and write it like this. So somebody apply the rule and tell me what should I write here for help. Deborah.
So, is it 3, and then in parentheses, -3x to the 4th plus 4, close parentheses, to the -1, then d, -3x to the 4th plus 4 over, dx.
Perfect. Perfect. Perfect.
That was nuts.
Which one?
Yeah, that is even.
Yeah, sorry, bad name, right? Perfect, perfect. Questions? Can't see it, you just talk, you don't have to even ask a question, you just say, I gotta see it again, or whatever.
Okay, so the n is 3. How do you know that
Perfect.
the n is 3?
Okay, so what she recognized to start with was she went again to her rule sheet. You'll use this a lot, that's why I gave it to you on a cardstock and a sheet protector. She identified that the situation we have is ddx of something to a number. She comes back here and says, okay, according to the rule sheet, the ddx of something to a number, the derivative of something to a number, it's called the power rule. You tell me, Jeff, what's the number and what's the something?
Oh, 3.
So 3 is the number.
Yeah. 3.
What's the something?
And then the something would be the thing with the.
Just say it all, what is it?
The -3x plus 4.
Good. It's whatever's being raised to that exponent.
Okay.
So then equal means same as. So we can replace this with something that's equivalent, which means we write down the 3, write down the something, 3 minus 1, derivative of the something.
Makes sense.
Perfect.
So is there kind of 2 separate things when you solve it? Like is the n something n minus 1 one part and then the d over the other?
Oh, well done.
Like, or is it all times together?
I know, that's well said. 2 comments there. First of all, what you see here is actually, I would say, 3 things being multiplied. Someone read my mind, raise your hand and tell me, what are the 3 things that I see being multiplied right here? What are the 3 things that are being multiplied? Let's go quick.
3, and then the something, the 3x, -3x to the 4th plus 4, 2 to the 3 minus 1.
Perfect.
And then the d over dx, and then the something.
Oh, close, close. 2 tickets.
Oh.
Remember, ddx is never, this is never multiplication.
Well, I'm saying like that section.
Oh, this whole section,
Yeah.
sorry, I just want to make sure. So make sure you realize that it's not d times anything. So,
Yes.
good. So there are 3 things being multiplied. Is that part of your question? Good. I kind of think the other part, I'm not sure, Heidi, is this. Okay, when we started this problem, we applied the ddx operator, the derivative operator, to one entire function. Okay. We won't ever in our class just go find the derivative of this whole thing as like one thing. That's too hard for our class level. We instead use the rule sheet, so this rule sheet here. We use the rule sheet to break up the problem into smaller and smaller pieces. So the first rule allowed us to do part of the result. This part is done. There's no ddx operator right here. So we're not going to do any more derivative operations on this piece. We still must use the ddx operator on this piece. Basically what we've taken care of is the exponent, the 3. And now we're moving on to take care of what's inside, what was being raised to that exponent. That's what we've handled so far. I'm not sure if that was your question, but you okay? Anybody else? Please, sorry.
So the something, is that the original function, like the -3x to the 4th plus 4? Is that what the something is?
Oh, good question. The original function is actually -3x to the 4 plus 4 all cubed. So the original function is everything including the power. This magical word something is just kind of my habit for understanding the situation. So when I look at the original function, what I see, Soren, is I see some function, which I sometimes refer to as just something. So I've got this function being cubed. And the power rule says that if you're trying to find the derivative of a function, being raised to a power, you can use this. And that's what I did. Did that answer your question?
Okay, so then shouldn't the second negative 3x to the fourth, shouldn't that be cubed?
Oh.
Why is that not cubed?
Awesome. Simply because the rule does not specify that it be cubed. I've got some function being cubed. The derivative of that becomes 3 times that same function now just being squared, multiplied by the derivative of just that function. So the cube is not a part of it any longer. Did that help? Yeah. Good. What else? Landon?
So, kind of going along with what Soren's saying, we're using the power rule because it's raised to a power, right? So like there's a power in the original equation.
Close, close. The original function, the function we start with, really is simply some function to a power. It's nothing else.
Yeah.
That's why we start with the power rule.
Yeah.
For example, if we had started with, say, the tangent of negative 3x to the fourth plus 4, we would have had to have started with the tangent rule.
Okay.
I don't know if that answers your question.
Yeah.
Keep talking, doing really well. Anybody else? Awesome. Now it's time to do the same thing again, but the situation now is different. So this kind of answers both Soren and Landon's, what you're talking about. So look here, the ddx operator is now being applied to this situation. It's no longer really a situation where we have a power function, because this is only being raised to the first power, and we won't use the power rule in that case. We'll use something else. So look at the rule sheet, everyone. This isn't something or some function to a power. It's now really a different situation. And again, you don't have to look at sine or tangent or cosine, but what rule, just looking at the sheet, does this seem to apply to? Sarah?
The add subtract rule.
Nicely done. Perfect. The add subtract rule. So let's write down that rule. So the add subtract rule says if I have the derivative of d over dx of one function added to another, that will be the same thing as the derivative of each function separately. Questions? Please.
Okay, so you're just looking, so there are two different functions from prime up here on the blue, so those two just can separate?
Right, because they're separated by addition. So what I can do, Jeff, is I can identify, here's what I'll call the function f.
Okay.
That's just a temporary name.
Okay.
You okay with that?
Okay.
And here's what I'll call the function g. Just don't mix that up with the fact that we said the entire function was called f. This is just me kind of temporarily calling this thing
Okay,
f.
but with those problems, you can separate them into two.
Yes, because they are separated by addition.
Okay.
If they are separated by subtraction, I could also separate them.
Okay.
Anyone else? Please.
We're just dealing with that right side.
This portion here.
Yeah.
Yes. This side, there's nothing left to do.
I mean, like.
Oh, sorry, this part.
Yeah.
Yeah, perfect. Look up here. Hey, look what Sarah said. Somebody answer this question. I'll answer Sarah's question. In this entire expression, what is the d over dx operator operating on in this expression here? Somebody help. Like, just read it. What is the d dx operator, Lexi, operating on?
The negative 3x to the fourth.
Perfect, and that's it. The d dx operator is not operating on this piece. So we're not going to do anything with this. We're just trying to figure out how to handle this d dx operator. So this part's done. We don't do anything else with it. Is that a good question? Good. Anybody else? Okay, so we applied the add subtract rule. Something to note. Here there are only two things being added. You could have multiple things. There's no limit. Like you could have 5 things being added, and the rule would still apply. You just break it up into 5 separate things. So let's see. Let's write another line. And don't get lazy. Write exactly what I write. I'm going to go back to the symbol dy dx just for emphasizing that they're the same. This part, you must rewrite it. Don't get lazy and put tick marks or something. You're practicing in part for the written portion of the AP test. If you use the wrong notation, they're going to throw your test in the garbage. Okay, because part of what they're testing on is, do you know how to use proper mathematical notation? And they don't go for student creativity. So, we got it? So I need to rewrite this. Look, here's a common mistake. Heidi figured it out already. We started with 1, 2, 3 things being multiplied, right? So whatever this becomes, it's got to multiply by this stuff. So put a big parenthesis right there. Somebody use the add subtract rule here and tell me how to rewrite this using the add subtract rule. So Sarah's in for 2, Oakley's in, Ellie's in, Sarah's in, Deborah, Graydon, Lexi, Heidi, anybody else? Soren's in. Go ahead, Jackson, what do I write?
Would be d to the 3 minus x to the 4th over dx.
Keep going, doing great.
And then plus d4 over dx.
Perfect, perfect. 3 tickets. Question. Perfect. What you should be seeing is that the ddx operator is just kind of, the way the rules work, is the ddx operator just kind of works its way through the entire function. On the very first step, the ddx operator basically took care of the exponent. Then the ddx operator is operating on this stuff, which was what was being raised to the exponent. Now the ddx operator is operating on each piece. These problems, that's how they'll always work. The ddx operator just kind of worms its way through the problem. That's how the operator was created.
For the test, we have to have these memorized for weekly.
You will have to have them memorized. The comeback I have to the groan is, remember, the median score was 85 to 88. This seems really intimidating when we start. It isn't by the time of the test.
Okay.
It just, you have to trust me because I've done this for 11 years. Everyone groans on the first day. By the time we take the test, it's not the formulas that are any sort of barrier. So.
Oh, that notation is only one way to apply because it also says f prime plus g prime.
Mm-hmm.
So could you just also put in that notation instead of?
Let me talk about that. Perfect, Deborah. Hey, look down here. You should note on the blue card that this is the same as this, and the blue card also points out that you could also just write f prime plus g prime. Those are the same thing. You won't really use this notation in this type of a problem, though, because it doesn't help. Because we really have to use the operator. So, good question. Anybody else? This will show up in some future problems, Deborah. That's why I put it on the card. Okay, we need to handle this piece right here. So let me show you how that works. Let's give a little more space here on the right. Okay, d of 4 over dx. It literally means find the derivative of the function y equal 4. This means find the derivative of the function y equal 4. So someone please raise your hand and tell me, what would a function look like if the function is just y equal 4? Great.
It'd be a vertical line at the point y equals 4.
Horizontal, but
Oh, yeah.
no worries. Okay, Braden, stay with me. That's the function y equal 4. 3 for Braden. Somebody else. What does derivative mean? Like we're taking the derivative of this function. Sarah, was it? Perfect. Tangent, slope, tangent, slope. Somebody else help me. If I start here, and I want to find the tangent slope at this point of this function, what do I find for the tangent slope at this point? 0. Questions? What is the tangent slope at this point? Say it. At this point. 0. So what is d of 4 over dx always equal to? 0. The derivative of a constant is always 0. You can memorize that. I didn't put it on the sheet because it's a little too simple to have a rule for. I don't think I put that one on there. The derivative of a constant is simply 0. So right here, this is 0. So we have dy dx. Make sure you keep writing equations. This part we just rewrite. Please don't ever distribute the 3. Don't ever distribute the 3.
Why?
Totally illegal. But no, 3 points for asking. I want you saying why. I always want you saying why.
Yeah,
The order of operations, Landon, require that you do the squaring first,
Okay.
and then do the multiplication, hence illegal.
Okay.
Also, a common illegal thought is this. Simply take the 2 and apply it to this piece, and the 2 and apply it to this piece. Also totally illegal. Felony in all 50 states and the territory of Puerto Rico. So, questions? Please.
If we go back to this one, the D4 over dx. So just because it's on a horizontal line, and is it a point that's from D4 over dx?
Oh, yes. Yeah, d4 over dx means what's the derivative, what's the tangent slope at any point of the function y equal 4.
Okay, and because it's a horizontal asymptote, it's always going to be 0.
Horizontal line, not asymptote, but horizontal line, the slope at any point along this function is always 0, hence the derivative of that function is 0. Perfect. Anybody else? Outstanding. So we took care of this piece. So let's write that down. Please.
So I'm actually not quite sure where you're going.
No worries, just talk.
Okay, so, but does all of these equations have a connection? Is that what you're saying?
Yes.
Okay, so every single equation on here has a connection.
They have a connection in that they are all showing how to find the derivative or a formula for the tangent slope of different types of functions.
Okay.
Yep. So when we first introduced the word derivative and I started putting graphs and things on the board, a common question was, are we going to learn how to actually find the numbers? Because we didn't really learn how to find any numbers in the first unit. We just had lots of graphs and things. This is where we're finding the numbers. So this unit's all algebraic, not a single graph. So no words in this unit either, only equations. So it's a little different. No words, no graphs, no true-false questions, no which of the following are true, no, only equations for this unit. It's a good break. I'm gonna have a question. You good? Okay, we need to figure out what rule applies to this situation. Now here we've got ddx of negative 3x to the 4th. Huge hint. A common error is to think, actually somebody answer this question. What's being raised to the 4th in this situation? Go ahead. Say it louder, that was good. Just the x, not the negative 3, just the x. So look at your blue sheet and see if you can find a formula, a rule that matches up with a derivative of something like this. If you guess wrong, I'll still pay you. I just want people talking. Sarah, what do you think? The exponential appears to be kind of like the right idea, but the problem is this one. The exponential rule looks like this, Sarah. We've got d over dx. A represents some number, some value, to an exponent. We really don't have that situation because we've got a variable to a number, where this is a number to a variable. So that's not quite right, but good try. Ellie.
Is it the power rule?
The power rule, if you remember, was this one. It's close, but not quite. Ellie, if we're going to use the power rule, we have to identify the exponent, which would be what? The 4. And then we also have to identify the base, like what's being raised to the exponent. What would that be? That would be x. And so the only reason we can't use the power rule yet is because we haven't done anything to take care of the negative 3. So the ddx of this whole thing, we got to handle the negative 3 first. So let's go talk. The constant rule is the one we want. So we'll erase this. We want this rule here that says d over dx of a constant multiplied by a function is exactly the same thing as the constant multiplied by ddx of the function. Anyone have a question of why Todd chose to use the constant rule?
Yeah.
Its process of elimination can really help. We've got negative 3 multiplied by something to a power. So if I look at the rule sheet, I can quickly say it's not ln, it's not e, it's not square root tangent, it's not a to it. Like I can eliminate all of these possibilities. Is there any question about getting rid of those very quickly? Please, Jeff.
Why is it not the product rule?
Oh, awesome. The product rule really would work because you have negative 3 multiplied by this x to the 4th. You're just going to follow my advice, which is when one of the multipliers is a constant, the constant rule is just easier. If the other multiplier were a function, we'd have to use this. Perfect. Other questions?
What did you say?
In this case here,
Yeah.
simply a different function.
Okay.
So this could say f times h, f times k, just two different functions. What else, please?
Constant in this.
Got it. In the example we're working on, Kelsey, the constant is simply negative 3. So what we have is we have negative 3 multiplied by a function which is x to the 4th. That helps.
And then do you just still say plus the 0?
Yes, because that's separate. Yeah, we're working on this piece, whatever this happens to become, that's going to go here, and then it'll still be plus 0. Perfect. Anybody else? Awesome. So we need to apply this rule to exactly this situation. So someone tell me what I should write here. Applying the constant rule to this. So we're going to rewrite that here. So Deborah's in, Kelsey's in, Soren's in for 2. We got Sarah, Oakley, Jeff. Who else? Sarah again. Heidi says maybe. What do you think, Heidi?
What would the constant be, negative 3?
Perfect. So we write that down first, just following the rule. Does that make sense?
Yep.
Good. So I go negative 3, and then after writing the negative 3, Heidi, what would you write?
This is where I'm not sure.
That's okay, let me help you. So when you start here, simply identify, it's really just like a visual map. We've got d over dx, here's d over dx. We have some constant value, negative 3, multiplied by some function. So what's the function in our example? X to the 4th. So equal means same as. So instead of writing this, we write negative 3 ddx. And what comes out to the ddx, Heidi?
X to the 4th.
Perfect. Does that feel reasonably logical? Good. What else? Please, Sarah.
Could you write the, and then have the x, is the x to the 4th supposed to be closer or?
Oh, great question. Okay, look up. Hey, look. You really have several options as to how you write what I just wrote. This is legal. It's saying ddx of x to the 4th. You could have written like this. D over dx, parentheses, x to the 4th. You could have written just dx to the 4th over dx. Any of those three is legal. Is that your question? Say it again.
With the negative 3.
Again with the negative 3 in front. Yeah. Deborah?
You always, like, do you have to keep the plus 0 always?
No, I wrote it just for emphasis. I'm going to stop writing it in a second. Please, Joe.
So when it shows the f of x, that's just the d over dx, correct? I mean the f, it shows the f right there in the,
Hold on.
So how it says constant f, that's the d over dx, correct?
No.
Or is that the x over to the 4th?
So the d over dx is right here. D over dx.
Okay.
So it's d over dx of this stuff. Okay. Just like it's d over dx of this stuff.
Okay.
So
Equals
equals this
that.
stuff. Equal means same as.
So the equation, so you get that, so you get the, so you get this new function, the constant d over dx, and then f to f of x. You put everything into that from the last equation, and then that leads to another one.
Yes.
Ah.
Yes, hey, listen. Yeah, Jeff, and everyone else. The way the derivative operator rules work, it's all about, like I keep saying, equal doesn't mean here's the answer, equal means these are the same. I want that, what was that up to? With your eraser. Equal means same as. So, what we identified was, Jeff, using the left side of the rule sheet, we said this matches up with this on the left side of the rule sheet. Because equal means same as, we're going to translate what's on the left side of the rule sheet into what's on the right. As we keep doing that over and over again, this, I don't know how else to say it, but this little operator just kind of weaves its way through the entire function, operating on every part of the function. In the very beginning, the operator was applied to the entire function as a whole. Using the power rule, we really only took care of the exponent portion of the function. That got us this much. Now we're going to operate on these two, so add, subtract broke those into two separate pieces. The derivative operator working here became just 0. Now we're working on this. We use the constant rule to break it down further. The -3 no longer has a derivative operator. We're done with that part. Now we're working on just x to the 4. Other questions? So what rule do I apply to d over dx of x to the 4? Kelsey?
The exponential rule.
You're close, it's just a little bit backwards. The exponential rule works when you have, we haven't seen an example of that yet. The exponential rule works when you have a base, which is a numeric value, like say 5. And the exponent is some expression. We have just the opposite. We have a base that is an expression x, and an exponent which is a fixed value 4. So that's the power rule. And they're not opposites, but they kind of look like opposites. 3 points for Kelsey. It's a good observation. Like here, you've got some expression raised to a number. On the exponential rules of Kelsey, you've got some number raised to an expression. You understand the difference?
Yeah.
Good. Other questions? So we use the power rule. So someone, come over here, I write it down, dy dx is equal to 3 parenthesis -3x to the 4 plus 4 squared -3. I need to operate on this. What does this become using the power rule? Abraham. Sorry.
So wouldn't it be 4 and then d over dx?
Let's look together. You're making a small error. No worries. So we're using the power rule, Soren. To use the power rule, we can see the ddx right here. Here's the ddx. We've got something, some function to a number. What's the number? 4. What's the function that's being raised to the number 4? Just x. So using the rule, we write down the exponent, which is 4, multiplied by whatever that function was that was being raised to the, so what goes after the 4 x. What exponent is applied now? 4 minus 1. And then what do we multiply lastly, Soren?
dx over dx.
There you go. 3 points for Soren. Question? Please.
So will that reduce to 1?
Perfect. It's not d divided by d or x divided by x. That would be wrong. But it is dx divided by dx. And something divided by itself is equal to 1.
Does the 4 minus 1 go to the 4 and the x or just the x?
Say that better?
Does the 4 minus 1 go to the 4x or just the x?
Yeah, you never close that first.
Right there?
Yeah. Well, no.
Keep talking. I know what your question is. Just sitting in.
Okay, does the 4 minus 1, does it go to 4x or is it just going to x?
Got it. Perfect. you'll answer the question if I just give you a minute. Okay, the exponent here, which is really 3, applies to only what is designated by the parentheses. So only the F. So just the F, not the K. And if you look at the rule here, Paris, same thing. This is only applied to what's in the parentheses. Good thing?
Yeah.
Perfect. Anyone else?
Why did we use the power rule?
Because we hit a situation here, Oakley, where we had ddx of some function, really simple function, just x, to a power.
Okay.
That fits this situation perfectly.
Okay, so that in the parentheses means.
Just the x in this case.
Oh.
Earlier it was something more complicated, this time just x. We gotta hurry a little bit, everybody okay? You're almost there. Hey, look up, look up, look up, look up. It's crucial that you note the following. Hey, it is crucial that you know what is being multiplied now. Look up. Look, you've got 3 multiplied by this whole thing. Multiplied by -3, multiplied by 4, multiplied by x cubed, multiplied by 1. When you have 1, 2, 3, 4, 5, 6 things being multiplied, you can choose to combine any of them that you would like. It's totally up to you. But we only combine things that easily combine. It can be written in a simpler way. So I can take 3 times -3 is, say it. Good. -9 times 4 is? That was a little slow, but whatever. -36. Sweet. Okay. So we go dy dx. -36. It is tradition to put this term earlier in the expression, so I will. Doesn't have to, that's just tradition.
Oh, you don't put it.
Wait, you can multiply even when they're in different sets of parentheses? Or is there like one big one that?
Great question. Chad, here's the answer. The parentheses simply mean multiply.
Yeah.
So if you look closely, inside here it's just 4 times x cubed
Yeah.
times -3, all times 1. So there's no addition, just everything's being multiplied. So I can just choose to multiply whatever. That's how multiplication works. So,
Is that it?
we've got, don't leave yet, don't leave, talk to me, what's your question? So look here. Okay, what's messing you up is this, watch me close, don't leave, watch. Okay, these parentheses are crucial, this is what Chad's talking about. These parentheses indicate that this whole thing is being squared, you can't get rid of those.
Yeah.
But over here, these parentheses here, just to make sure I don't mix up the negative with the 4, make it think it's -34. But it's just -3 times 4 times x cubed times 1. Those are just there's 4 things being multiplied. So I can put them all together and get -12x cubed. That times that would be -36x cubed.
Hiram
Yeah,
Silo,
That's just what that first.
Haley Smith,
This is one.
Jocelyn
What's
Stevens,
mixing you up is this. Listen, this is your algebra
and
student.
Rachel
Don't worry about it. Very weak. Hey. All I have here, Elliot, is 1, 2, 3, 4, 5, 6 things that need to be multiplied. The order of multiplication doesn't matter, so I just multiply things that easily multiply, and I just go there in whatever order I want.
So basically from the beginning to
Mom.
the end, out there.
Yes. Notice, yes, yes, yes. Hey, there's no derivative operator here anymore.
We're done.
We're done.
So that's the answer?
Break my dollars. That was way too hard to get there.
It took years.
Let's take formula. Everybody is slow. Once we start, I'll ask
Yeah, I was there. So,
Okay, so good.
that was pretty good.
Then you can
So that's C.
We have revisions, the whole country, or
Yeah, but to square them, this whole thing.
Maybe we just do
That's
another
why
side.
it's
State every year.
That's after
We
state,
don't
that's my
ever do that in
birthday.
our class.
I do
There's no
that
reason
for
why
my
you.
18th birthday, I'll be driving
Yeah,
there.
that's legal, you just don't talk about
What is
it.
your birthday?
November 17th.
Oh, I'll probably remember that.
Oh!
I might, wait, which
Oh,
day is it?
It's the Thursday after that.
That might be Wednesday or something. Oh, I'd be doing it.
To be there.
Yeah, good luck. Good luck doing all of those steps on there. That's why I told you to get out of that.
Oh, I'm supposed to go. This is go to Mason. I'll watch you guys.
Well, I'm going to the races. I don't know.
This can't be
Wednesday is that?
so we no longer need to use the blue sheet. If you wanted to, you can do some more stuff here, you just don't want to. Simplify is kind of a nasty word. Really, all you're doing is you're writing things in there. Whether you want to do that or not depends on what you're going to use it for. So you don't really know what we're going to use this for yet. So you don't want to say, let's write it in one form, maybe this form is what's useful. So no, you just. You're welcome. Good job, you guys.
That's all the stuff that requires. I'm sitting in there, it's too messy for me to look at.
Oh.
I work on some spreadsheets right now.
Yes. I won't necessarily be able to help you, but you're welcome to work, Kelsey.
Are they right there?
Yeah. No, you're always, you can say any day you want, Kelsey.
Okay.
I just can't always help. I just apologize for that.
No, you're fine, you're fine.
Good morning, guys, and welcome back to school. This is Braden Bromley. And Karen Boyington, please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America. And thank you, and here's Principal Bromley. Good morning, students. It's going to be another great week here at Lone Peak. Just want to remind everyone that next Wednesday, so a week from this Wednesday, is the end of the term. That's October the 19th. So thank you for staying caught up on everything, your grades and your attendance. Of course, that is the day before fall break. So everyone dig in and work really hard, and then you'll have a nice break to gear up for the second term here at Lone Peak. It's Monday morning, so we're excited to announce our Students of the Week. We want to congratulate from 10th grade, Mackenzie Bidey, 11th grade, Jaden Landon, and 12th grade, Bentley Walden. Congratulations, and we appreciate your hard work and what you contribute to Lone Peak. Last week we did a good job updating you on our state championship golf team. Want to just update you on a few of our other sports that are going on right now. Our girls tennis team did a great job representing Lone Peak last week in the state tournament, and we took second place in the state. We want to congratulate both of our doubles teams that won first place. So that's our first double teams, Tammy Gracious and Rachel Neeleman, and also our second doubles team, Katie King and Ellie Sliding. Congratulations, they took first place in the state. Other team members that contributed to our second place state victory were Daniela Aaron, Anna Aaron, and Jocelyn Seberg. So congratulations to our tennis team, we're so proud of you. Also want to update you on soccer. Our soccer team took a second place in the region, and we start the state tournament tomorrow. We play a home game tomorrow at 4 o'clock against Skyview. So that's the first round of state, so everyone come and support our soccer team. Cross country last week had the region tournament, and both our girls and our boys cross country teams took second place in the region. Great job. They're moving on now to state, and state will be a week from Wednesday, so the last day of the term, October 19th, and that will be at Liberty Park up in Salt Lake. Our volleyball team is actually in the middle of region play, but they're doing great. They're #1 in the region as of right now. Want to remind everyone that this Thursday is going to be Big Pink Night at the home volleyball game. So there'll be free Chick-fil-A coupons to the first 100 people. We want to encourage everyone to wear your pink and come out and support our volleyball team. Then finally, our football team is doing great. We're also ranked #1 right now in our region. We're undefeated in region play. Our home game on Friday is against Woods Cross, and we're actually having a police officer and fire department appreciation night on Friday night. So at halftime, we'll be honoring the men and women that are very brave and that sacrifice for us to keep us safe. So that'll be happening at halftime at the football game on Friday night. So all our sports teams are doing great. Congratulations and thanks for representing Lone Peak. We're also proud of our Shakespeare team. They went to a competition in Cedar City over the weekend. We want to congratulate Oakley Thacker, Zach Elvey, and Connor Bates, who won first place in the duo, trio, scene competition. We're so proud of you. Great job. Also, congratulations to our dancers. Our ensemble team took third place, and our trio took fourth place. That's actually student choreographed, and we're very proud of Mallory Kraft for choreographing that. So great job to our Shakespeare team. Lots going on this week. Students, thanks for working hard. Again, end of the term is next week. It's going to be a good week here at the Peak. Here's your president, Braden.
Hey Knights, remember this month's Shield of Honor is Valor. Nominate people who show valor by texting LP Shiv Corp to 81010. These students will be recognized at the end of the month.
Alright, the Sir Night Pageant is tomorrow night at 7 p.m. in the auditorium. Tickets are $5 and find a member of the drill team to buy them. You can also pay at the finance office or at the door.
Hosta Club General Membership Meeting is Tuesday, October 11th at lunch in room 602.
Alright, Sadie's is on Saturday. It's from 8 to 11 in the Fieldhouse. The cost is $15 in advance or $20 at the door. The theme is, it was a dark, stormy night. Costumes are optional. You could just wear matching shirts, whatever you want, but there's no masks and the dress code applies. And you are not allowed to dress as clowns, so don't dress as clowns. Alright.
Attendance school is happening now. If you have an NC, get it cleared ASAP. See your advocate for more info.
And remember, Knights,
this is our kingdom.
put on kind of soft music, if
Yeah.
it bothers you, you just say, I can't concentrate.
No, you're fine.
Right,
You're fine.
making
I
sure.
listen to you, you're fine.
Because I actually can't do homework if there's music on.
That's how I am, that's how I am, no
All right.
problem.
Very good.